everyone. This is Lena.
This is Natalia. And we're going to talk about distributed algorithms because they're not really intuitive. So if you have any questions, feel free to come up to us after the talk, and we'll answer them. But right now, we're going to cover lots of material, so we might not have time for questions. And the code will be available on GitHub. So why do we even need to look at distributed algorithms at all?
Well, why do you need to know algorithms in general? You might not need to. You might be doing pretty good without knowing the underlying nuances.
To oversimplify, it's like with sorting algorithms. There is a whole bunch of different sorting algorithms that provide different performance for various scenarios.
Yeah, and we're not saying that everyone who uses distributed system needs to know what is consensus or failure detection or gossiping. You can successfully use a distributed system without knowing the underlying algorithms. But in some cases, it's really useful to know and understand how a system works on the inside, how it's built. For example, it helps to better understand guarantees system provides and to be ready to address unhandled cases.
Things will break, so understanding will actually help you determine the cause of the wrong behavior of the system based on its symptoms. And it's really hard to debug distributed systems because weird errors you usually get are sometimes crazy tricky to find and track down. And blind attempts to fix something in these cases might be not the very best use of time. Sometimes seemingly misbehavior of a system is not actually a misbehavior, but we're thinking that it's an error because we don't have a full picture.
So what you're saying is it helps to be better at tuning configuration to avoid blind troubleshooting attempts.
Yeah, because tuning of performance, consistency, or latency, these are the things that are most complicated to solve and troubleshoot.
Yeah, and it's also useful when you want to understand how your system is going to behave in edge cases when conflicts are possible. And to enhance and improve existing distributed systems, or maybe even write your own new distributed system.
I guess it also helps to look at it as more of a white box instead of a black box, because lots of distributed systems of tools are actually open source. So you can look at the code online, and knowing algorithms will help you understand it and possibly contribute. So let's look at the websites of most popular distributed databases. So we see things like high availability, scalability, performance. So these things are really good, and it sounds exactly like what we need. But what does it really mean?
As you probably noticed, there is a prevalence of abstract words like for mission-critical data, performant, fault-tolerant. But at the same time, we could spot some brief mentions of more concrete terminology like strong consistency, linear scalability, hinted handoff, read repair, and so on. So behind vague abstract words, there are some very specific and concrete algorithms that system uses. And product vendors and creators actually mean those things, but they try to encapsulate unclear terminology to words that broader audience will understand.
Yep. We're also trying to enforce some of the distributed system properties. For example, safety means that nothing bad should ever happen. Clients should never read a stale value from our system. And liveness, which simply means that something good should eventually happen. So if we're waiting for a response from a node for 2 hours and we haven't received it yet, we will eventually receive it. So how do we get liveness and make sure that our system is available? We can make all of our operations asynchronous. We can decentralize responsibility or avoid any lock-in and waiting.
But it decreases the consistency of our data.
Yep, and to get consistency, we can choose a coordinator node, make sure that the update is propagated to all of the replicas. We can choose the full synchrony, but it's not really performant. So it decreases the availability of the system a lot.
But we don't have to completely refuse from one or another. We can choose to have some of each. And system properties such as consistency and availability can be tuned. So we will show different algorithms that provide different types of guarantees for different purposes.
Our system should also be ready to react on events or recover from all sorts of changes or failures that can happen. For example, what if a node dies or connection is interrupted? We should be able to detect this failure, and we can use failure detectors to do that. What if a node joins? We need to be able to notify the rest of the nodes about this, and we can use gossip or anti-entropy for this. We need to be able to recover from failures. We can use snapshots for checkpointing or recording of a global system state. And there is a whole bunch of other things. So we'll start with the basis of every distributed algorithm, which is consistency levels.
So data is replicated so that success of read-write request doesn't depend on availability of any particular node. So when some item is changed, its updated value must be propagated to all of the replicas. And system is consistent when concurrent requests get the same value for the same data.
But how can it happen that there are two different values for the same entry in the same system?
Well, imagine a situation when someone updates the value and it starts propagating to the replicas. But so far, the update hasn't reached all of them. So some clients may get the most recent value because they contacted the updated nodes, but other clients may get stale data from the replicas where update hasn't propagated to yet. So eventually, these replicas will get in sync, which is called eventual consistency. But until that happens, the state of the system is inconsistent. Different clients may receive different values for the same data. Good news is we can kind of choose the level of consistency.
But can't we just choose the best level of consistency all the time?
Well, consistency is important, but there is a trade-off. A system with better consistency is less available. So let's look at different consistency levels and how they affect our system. Let's start with weakest consistency level. Client synchronously writes to any replica, and client is done at this step, implying that update completed successfully. However, node that received the update asynchronously sends new data to some of the replicas, which update their info and continue to spread it to the rest of the replicas. And new client can connect to any node for reads, whether it's up to date or not.
So advantages here are we get super cool availability and low latency for reads and writes. But as a trade-off, we get low consistency because of the high propagation time, which is the time it takes for an update to spread out to all of the replicas. And because the update is first written to one single node, if it fails, there is no guarantee of successful data exchange.
Yeah. So to reduce propagation latency, client can send asynchronous requests to all of the other replicas directly.
But what if a node fails during the propagation of the update? Then this update might not be delivered at all or until some occurrence of scheduled repair process, which can take a long time. For this case, we can use a technique that's called hinted handoff. So if some nodes fail during the time when some other node tries to replicate a new update, a coordinator node or some other node can create a hint. So a hint is a special file that stores data that was supposed to be for a node that's failed. So when it comes back up, the data consistency is recovered, and so everything works well. But what happens in case coordinator fails or hint file gets corrupted?
Well, In that case, we can add an independent check for inconsistencies called read repair. Each read or randomly selected reads can trigger an asynchronous process that requests a digest, which is like a hash or a signature for the requested data from all of the replicas. And in case of some differences, they got fixed.
So I guess this process runs on reads, so it's going to be a bit of a hit on availability.
Yeah.
But can we get a stronger consistency?
Yeah, so to have stronger consistency, we have to sacrifice availability and guarantee an overlap between sets of nodes where client reads and writes data. So client synchronously writes to some specific number of replicas instead of one, and touches some other specific number of replicas during reading. And these numbers are called write and read quorum. Different values for write and read quorum allows to trade write latency to read latency and vice versa. However, write quorum has to be greater than half of the replicas, and sum of write and read quorums has to be greater than number of replicas overall. Why? Let's imagine a situation when we have a cluster of 5 nodes, and we decided to have 3 as a number of synchronous writes and 2 as a number of synchronous reads. 3 plus 2 is not greater than 5. So if all asynchronous requests fail, we may have stale data from our replicas. So by following through, we ensure that at least one replica will have fresh data during read operation. Client will use it.
Cool. I guess the more real-world example is, imagine a family with 5 kids who are quintuplets, so they look the same, and parents don't really know who is who. And one day, they asked 3 of them to calculate the approximate estimation of Cassandra partition size. And 3 of them actually did it, while the rest of them didn't do this. So when they came back home from work, they've asked 2 random kids to provide an answer. And these 2 kids happened to be those who didn't perform the calculation, so they didn't know the answer. So if parents were smarter, they would ask 3 of them to calculate it, and one of them would be the person who knows the answer. Yeah. So far, we've been looking at approaches of how to detect inconsistency. But we can do something to prevent inconsistency also.
Yeah, so to prevent inconsistency, we have to have some kind of centralization. For example, master-slave asynchronous replication. All of the writes are directed to one central node, which performs writes sequentially. So it is a stronger consistency, but it is a hit on availability because master is a bottleneck here. Consensus is also strong consistency, and we will look at it a little bit later. So Cassandra and React use weak consistency level protocol for metadata exchange. They also use hinted handoff and read repair techniques. HBase uses master-slave replication, and zookeeper writes are also performed by master.
So now let's look at the actual protocol that implements the weakest consistency level.
Yeah. So gossip is a peer-to-peer communication protocol where nodes periodically exchange information. So this information can be real content, but usually it is configuration or metadata that nodes exchange about themselves and about other nodes in the cluster they have gossiped about.
Gossip is widely used in the real-world distributed systems, for example, for failure detection or for solving inconsistencies. Or, for example, when a distributed database topology changes, this update should be propagated to all of the nodes so that they operate accordingly and are on the same page.
It's also used when system needs to be fast and scalable, fault-tolerant, or extremely decentralized. So, general gossip protocol is the endless process of periodically selecting some node or a list of nodes and sending a message with some information to them. So eventually, all of the nodes will get this data. And in traditional gossip, all of the nodes have the same and full list of nodes to gossip with. But in some implementations, the first step is gossiping about this list of nodes to start gossiping.
But what happens if there are two different values for the same key gossiping in the same system at the same time?
Well, in this case, we can have some kind of version associated with the message, for example, like timestamp. So during a gossip exchange, all the information will be overwritten with the most recent one. So there is a technique that is used to solve the state of inconsistently replicated data, and it's called anti-entropy repair.
It's based on gossip.
Yeah. So nodes here periodically select some random node, and they exchange some data to synchronize data in their replicas. And in case of some inconsistencies, they decide which value is newest, for example, by timestamp, or they solve it.
So if you remember read repair, it runs on reads. So if we had some inconsistent data that is not read in days or weeks, it will stay inconsistent. With anti-entropy repair, we can actually choose when we run it. We can run it constantly or periodically or launch it manually. So it's like an independent check for inconsistencies.
Yeah, and also we usually exchange only hashes of data because of the message transmission size. And in case of hash inequality, well, then the actual data transfer takes place. So Cassandra, React, and DynamoDB all use anti-entropy repair technique to solve inconsistency of the data. And the all approaches are based on Merkle trees. And Merkle tree is a tree data structure which has hashes of data on the leaves and hashes of children on non-leaves. And branches of the trees can be checked independently without requiring nodes to download the entire data set. And also, different tools have different approaches on Merkle tree storage and creation. For example, Cassandra uses short-lived in-memory trees, while React uses on-disk and persistent trees. Oh, and there is another gossip technique. It is called rumor mongering, and it is used for data exchange. So all nodes are initially ignorant, but when a node receives an update, it becomes a gossip girl. And this gossip girl periodically selects some nodes, and it sends this information to them and enforces them to become gossiping girls too. So eventually, after gossip girl forwarded the new information to some number of nodes, or after some timeout, it stops being a gossip girl and just stores the update without forwarding it further.
So React uses gossip to communicate the ring state and the change in bucket properties. Cassandra uses it in failure detection and about changes in distributed topology. Consul is based on a protocol called Surf, which is also based on Swim, and it's used to detect new members or like failed nodes, and for reliable broadcasts in case events like leader election. And Amazon S3 also uses gossip to share the system state.
On the contrary, just imagine if we would have to rely on one poor node that sends information to all of the nodes in the cluster and waits for the acknowledgement. So it's really...
So there are some trade-offs with gossip. We have a really high propagation latency in some cases. If some data is corrupted, there is a risk of spreading it to the entire cluster. And also, if you need really strong consistency of your data, you probably need to choose some other protocol, not gossip.
Yeah. So let's look at the example, how it works. So here we have 5 nodes, and they all have a state of a favorite programming language. So they exchange their information, and they send different messages for different nodes, And eventually, they all will have this data exchanged.
Yes, so in this case, it's like a favorite programming language for each node. And eventually, we'll see that each node has received information about each other's node favorite programming language.
Here, yeah, we can see that everyone got it.
Yeah, and now let's look at some code, actually. Oops,
So here we have a gossip.
1 second, it's not on the screen yet.
Oh, sorry.
Okay. I guess you can see it now.
So here we have a gossip node, and it has a gossip period, which is a period when current node chooses a random node to gossip with. It also has number of nodes to gossip. Oh, sorry. And the state in this case is a favorite programming language. Gossip neighbors are the full list of the nodes in the cluster, like in traditional gossip. And we have different functions like continue gossip, gossip process. So in gossip process, it randomly selects some nodes and sends its state to them.
Okay. Let's switch back. Okay, cool. So gossip is a weak consistency level protocol, but sometimes we need something stronger. In distributed systems, there is a problem of getting some set of nodes to agree on some value, on some decision, on the order in which operations should proceed. And this problem is formally called consensus.
Yeah, so it turns out that in a distributed system with asynchronous message delivery, no algorithm can guarantee to reach an agreement if one or more nodes can fail by stopping.
But nevertheless, there are ways to work around it and to solve consensus in asynchronous system that admits certain number of failures. So consensus is a basis of distributed coordination services, consistent replication, and for example, leader election for some higher level protocol. The most famous implementation or like consensus algorithm is Paxos, which works in asynchronous environment that admits crash failures. Paxos is used at Google in their distributed log service, Chubby, to make sure that replicas are consistent. It's used in Apache Mesos in their distributed log coordination service. Also, it's used by Amazon. So there is a common theme around consistent replication. And the most basic Paxos variant is basic Paxos, which has proposers, acceptors, and learners roles. So proposers can propose values, acceptors can choose and accept values, and learners can find out which values have been chosen. So if a proposer decides to propose a new value, it creates a prepare request with a proposal number n and sends it to some set of acceptors and asks them to respond with one promise to never again accept a proposal with a number less than n, and to return a highest numbered proposal that the acceptor has ever accepted. So when an acceptor gets a prepare request, if its proposal number is greater than any it has ever seen, then it responds and does the promise and everything. So as soon as a proposer collected responses from a majority of acceptors, then it can create an accept request for a proposal number n with a value of highest numbers proposal it received from acceptors. Or if it hasn't received any values, it can choose any value to propose. So when an acceptor gets an accept request, it can accept it if it hasn't responded to a prepare request with a number bigger than n. So this one is basic Paxos to decide on one value or to make one decision. So what if we have a sequence of values? Do we just run basic Paxos in rounds until we make all decisions? Well, almost, except we can optimize it, and in consecutive rounds in Paxos, we can skip the prepare phase, and assuming that we have a stable leader. So it's called multi-Paxos.
Yeah, so multi-Paxos is the one that's used in production systems. And if you want to tolerate F failures, you need to have at least F+1 replicas for state durability and 2 F+1 acceptors for fault tolerance, because we need to have a majority to agree on a value.
Yeah. So there are a bunch of different Paxos variants. And for example, cheap Paxos. To tolerate F failures, we just need F+1 acceptors instead of 2 F+1 like in traditional variant. But in this case, if an acceptor fails in the fixed quorum, then there will be an auxiliary acceptor that takes its place so that there are enough acceptors. In fast Paxos, it reduces the speed for message delays when replica learns the chosen value. But here, it costs us 3 F+1 acceptors, so we need more acceptors to be faster. And vertical Paxos is reconfigurable Paxos that uses the auxiliary master to decide on set of acceptors and what is the leader for each configuration. There's also Raft, which is not from Paxos family, but it provides similar guarantees. It's used by etcd, which is used by Kubernetes. And its primary goal was to have a really understandable and simple consensus algorithm.
And there is also Zap, which is used in Apache Zookeeper, which is a famous service for managing configuration information, naming, providing distributed synchronization, and group services. So Zap provides better ordering guarantees in case when leader can fail.
Yeah. So now let's look at snapshots. So it's good when nodes can actually agree on some value and decision, but we should also be ready to deal with situations when something doesn't go right. So we would like to show the practical example of an algorithm implemented in F#. And we've chosen F# because it's a great functional programming language, and it's really easy to understand if you don't really are familiar with this. So the algorithm is called chandy-lamport snapshot. Here, any node can send basic messages to any other node it has a channel to. And any node can initiate a snapshot. And that means that it persists the local state and sends out a special type of a message called marker to its neighbors. And that means any node can receive a marker message at any point in time if there is a snapshot going on.
So when a node receives a marker message for the first time, it persists its local state and the state of a channel it received a marker through. So if it is the first marker a node receives, the channel state is empty because of the first in, first out ordering of the messages in channel.
Yeah, but when a node receives a marker from some other node after it has done the state snapshot, it means that some time has elapsed from the moment it has captured its local state until the moment it received another marker message. And there is a definite possibility that there, in the meantime, current node has already received some of the basic messages. And those messages, they can't be captured as a node state of either receiver or sender because both of them have recorded their local state. So these messages should be kept track of and recorded as a part of a channel state between sender and receiver. And the snapshot is done as soon as each node has received a marker from all of its incoming channels and recorded their state, local state and channel state. But it's easier to look when we have some sort of example.
let's imagine that each node is like some person's bank account. And node state in this case is amount of money in the account. So nodes can send some money to other nodes if they have enough money.
Yep. So it happened that Natasha decided to send $10 to Maggie, and Elena decided to send $5 to Natasha. Elena also decided to initiate a snapshot, so her node captures its local state and sends out a marker message to both Maggie and Natasha. Maggie receives a marker message from Lena, and it's the first marker she got, so Maggie's node records a channel state between Lena and Maggie as empty. Maggie also captures the state of her node, sends a marker back to Lena and a marker to Natasha. But at the same time, message with $10 from Natasha to Maggie is delayed and not delivered yet because of some network latency. But Natasha received her $5 from Lena. Then Lena receives a marker from Maggie and records the channel state between Maggie and Lena as empty. Natasha receives markers from Lena and Maggie and captures the local state of her node and state of incoming channels. Marker from Natasha to Maggie is ordered to arrive after this $10 message arrives because we need to assume first in, first out ordering of channels for this algorithm to work. So then, finally, message with $10 arrives to Maggie, but because Maggie has already captured the state of her node as a value of 0, she can't add $10 as a part of her state. So, and as Maggie hasn't received the marker from Natasha yet, she puts this message with $10 in the queue of messages to a snapshot in the future. And this is done to make sure that the $10 message will be captured as a state between Natasha and Maggie. So, and finally, Maggie received a marker from Natasha. She added $10 message as a part of channel state between Natasha and her. And at that point, every node is done, and snapshot is done at this point. So let's look. Here are these 3 nodes, basically the same as on the diagram. And each of them has some money in their account, and they can send them to each other. So as you see, nodes are recording their local state and the channel state. And let's actually look at the code here, too. Just need to switch the screens. OK. Here are some basic data types for data exchange. And the main type is snapshot node, which has state, snapshot state, and some of the main functions like initiate snapshot, receive snapshot message or like marker message, and it can send marker messages to outgoing channels, persist local state and channel state, and it's also based on top of a TCP server abstraction because we need it for like ordering of messages and channels, so we can receive and send asynchronous messages. And you will be able to look at this code in more detail on GitHub. So for now, let's switch back. It's good when we can. It's good when we can like snapshot things to detect the failure, but we need to use failure detectors to be able to actually detect real failures, not to recover from them.
Yeah. So in a cluster of a distributed system, it is important for nodes to know about failures of other nodes. Why? Then client won't be directed to the node that is down, or nodes won't be waiting for the reply forever. Also, it is a critical part to successfully accomplish operations like literal action, agreement, reliable broadcast, and so on. So how faults are detected? For example, in heartbeat approach, each node runs an agent that is responsible for sending heartbeat messages periodically. And if no heartbeat message arrives after some time from some node, it is added to the suspected list and considered failed.
Yeah, so there are two properties. Completeness.
Yeah, there's two properties, completeness and accuracy. So completeness states how completely nodes in the cluster eventually detect faulty processes. And it can be either strong or weak. So it's like how many nodes in the cluster are aware of all crashed processes. If, for example, we would have a failure detector that detects every node as failed, when it can be not failed actually, it will have strong completeness property, but it's useless in practice.
That's why we have accuracy property, which restricts the mistake and basically limits the number of nodes that can be mistakenly suspected by correct nodes. And accuracy can be strong when all correct processes are never suspected. It can be weak when at least one correct process is never suspected. It can also be eventual strong and eventual weak, which is basically the same, but nodes could have had wrong assumptions in the past. And by the way, here we use process and node as the same thing because of distributed systems terminology.
Yeah, lots of information. But there is a failure detector for each combination of completeness and accuracy properties, resulting in 8 failure detector types.
But we're not going to cover all of them, just some of them.
Yeah. So if failure detector has strong completeness and strong accuracy, this is a perfect failure detector. And it's actually only possible only in synchronous system because it doesn't allow any wrong suspicions.
Yeah, so here we say that failures are detected instead of suspected because assumptions about failures are permanent, so they don't change.
So nodes periodically send heartbeat messages to all of the nodes, and they also run like timeouts for each node. And if no heartbeat message arrives, then this node is detected as failed. It's like if Maggie would expect her friend Todd to call her every minute, and when he doesn't, well, she considers him dead and never changes her decision. There's also another failure detector, eventually perfect failure detector. It combines strong completeness and eventual strong accuracy.
So this one is for asynchronous systems.
Yeah, so the idea here is to also use timeouts and heartbeats, but timeouts now are adjusted. So when node didn't receive a heartbeat message within the timeout period, but receives it then later, then this node is removed from suspected list, and timeout for this node is increased to be maximum or average, for example. So eventually, timeout will be that big that all of the assumptions will be correct, which is exactly what is eventual strong accuracies.
So this is the actual example for this eventual perfect failure detector. So failure detectors are used in consensus, and depending on which type of failure detector we choose, we can tolerate different number of failures.
Yeah, and failure detectors are presented in almost every distributed system. For example, Cassandra uses Acroll failure detector, which outputs some kind of probability of the failure, but it's like eventually perfect one. So it's like if Maggie would store and analyze the information about Todd's health, like his heart rate and so on, and to output the probability of his death when he didn't call her.
Yeah. So Console and DynamoDB use SWIM, which is a gossip-based membership and failure detection protocol, which tries to use other nodes to confirm the failure of one node. So here, if Maggie called her friend Todd and he doesn't respond, then she would choose some of her friends and ask them to call Todd to make sure he's all right. So if Maggie didn't receive responses from her friends that he's all right, she would call all of her friends and tell them that Todd is dead. Yeah, so let's go to reliable broadcast.
So to work efficiently, systems should act like a single unit. So for example, values for the same data should be the same for each replica. But messages can be lost and nodes can fail. And luckily, we have various broadcast algorithms that help us to choose between consistency of our system and its availability. So let's look at the best effort broadcast. It ensures the delivery of the message to all of the correct processes if sender doesn't die during the message exchange. And actually, it's pretty simple. Node just sends messages to all of the nodes and using perfect point-to-point connection.
Yeah, so if a sender sends a message and then dies, there is no guarantee that this message was delivered successfully to its destination. So if sender was up, it could retransmit the message to make sure that the system is consistent, the message is delivered. But as sender is down, there is no way to make sure that system is consistent.
That's why we have reliable broadcast. It ensures that if any correct node delivers the message, then all of the correct nodes should deliver the message. So let's look at the example of its implementation. Message now has sender ID in the header, and when node receives the broadcast message, it starts constantly checking the state of sender. And when someone detects a failure, it relays the message to all of the nodes. So if failure detector marks sender as failed, then when it's not actually, then it will send unnecessary messages, and this will impact performance, but not correctness. But if node won't detect failure of a sender when it actually failed, then needed messages won't be sent.
So that's why there are some reliable broadcast algorithms that don't use failure detectors at all, and they assume the worst case scenario from the very beginning. And as soon as they get a message, that they immediately relay this message to other nodes. But what if a node receives a message, then processes it, and then fails? And assuming this message wasn't processed at other nodes, then the system is still going to be inconsistent.
Yeah, so that's why we have uniform reliable broadcast. It ensures that if any node received the message, doesn't matter if this node correct or crashed, then all of the correct nodes should deliver the message. And let's look at how all ACK algorithm works. Node that initiate the broadcast sends messages to all of the nodes. And each node that gets the message relays it immediately and considers it pending for now. Each node also keeps track of the nodes from which it received the current message. And only when process gets current message from all of the nodes, only then this message is considered delivered.
So we've covered consistency levels, gossip, consensus, snapshot, failure detectors, distributed broadcasts, which should give some idea about what kind of distributed algorithms are used in real systems. So, and feel free to reach out. Next slide. And thank you very much for attending. And the code will be on GitHub.